In this video, we'll be using this Little Brain++ board with an STM32 F4 microcontroller and a barometric pressure sensor to estimate changes in altitude. Thank you very much to Altium for sponsoring this video. The Little Brain++ we'll be using in this video was actually designed using Altium Designer. If you'd like to give Altium Designer a try for yourself, you can go to altium.com/yt/philslab. For more information, I also have various Altium design videos on my YouTube channel, and also one in particular which gives you an overview in 20 minutes of how to design this Little Brain++ board. Thank you also very much to JLCPCB for sponsoring this video. The Little Brain++ was manufactured and assembled by them, and in exciting news, they now offer standard PCBA rather than this economic PCBA, which is single and double-sided placement, which means you can place components both on the top and bottom of the PCB, which is pretty cool with some BGA stuff coming in the future. If you're interested in getting one of these boards for yourself or looking at the design, all of the Altium, assembly and Gerber files are in the Little Brain++ repo and my GitHub account, github.com/pms67. First of all, let's talk about how we even get altitude from pressure measurements. In essence, it's the basis that atmospheric pressure changes depend on the height. This is due to the weight of air above. So the higher we move up, essentially, and start from the Earth's surface and move up, the less weight of air is above us. So we increase our height and we decrease our pressure. The opposite is true as well. So if we start at a certain point above Earth, for example, and the lower we move down, the more weight of air will be above us. So as we decrease in height, the pressure will increase. And typically you will see plots such as the one on the right here, where we start on sea level on the left, so typically denoted by a height or altitude of 0 meters, starting at about 100 kilopascals, and this non-linear relationship as we increase in altitude, how much the total pressure drops. Therefore, if we find some sort of way that we can measure pressure, we can infer height from that. And it's always important to note that the height is always relative to a given level, and typically you will see that to be ASL, which is above sea level, but we'll use a different reference in this example. Then of course, naturally the question is, how do we even measure pressure? Now there are many different ways, and there's different types of pressures you might want to measure in different areas, not just atmospheric pressure, but for us, easiest and cheapest are what's known as barometric pressure sensors. Typically, they contain quite a lot of circuitry and sensors, so a piezoresistive sensor, which will give some sort of analog output, voltage or current, depending on the pressure. You can see that's usually with some sort of porthole, and the pressure sensor will be underneath. Temperature sensor will usually also be included for compensation, calibration, and so on. To get the analog output to be digital, in most cases you'll need some sort of A to D converter, processor which might apply some sort of linearization, filtering, and also provide a digital interface. So there's quite a lot of things in a simple barometric pressure sensor. However, luckily for us, because we're more of a higher level design in this case, we just see a package like this. And this is a very typical and common Bosch BMP 180 pressure sensor. We're going to be using something very similar, and the pinout might be something like this. We just have to apply power, so the VDD and ground pins. We can choose our interface, either I2C or SPI, and we can get digital data streams out. Once we have those raw pressure measurements, we need to think about how do we even calculate height. Usually two main methods. One is the first tier, it's this barometric formula where we need to know the temperature, we need to know the pressure, various other constants, gravity, molar constants, and so on. So quite involved. There's also a far simpler method, which is based on hydrostatics. So we have a change in pressure is a change in height times the density times gravitational constant. Now also notice the minus sign is because once we increase pressure, we actually decrease in height. So in both of these formulas and both of these methods, we have several problems. First of all, the temperature influences the density, it influences this formula directly. Density changes depending on height, gravity changes depending on height, and other different factors. So it's not as straightforward as plugging in, constants into here. The question is also, you see P0, P0 or P ground or H ground. How do you define these reference levels? What are these relative to? For simplicity, and as you've probably assumed, we'll just go with the hydrostatic method. We just need to know the density and gravitational constant, and for our sakes, we're just going to keep it really simple. Around sea level, the density of air is 1.225 kilograms per meters cubed, and the gravitational constant on the surface of the Earth is about 9.81 meters per second squared. And we're assuming these are both constant. All we need to do when we initialize our system is then measure an average pressure, which means we're essentially finding out P ground, so our reference level, which we talked about just a second ago. So we're collecting a number of samples, adding them together, and dividing by the total sample count, and that gives us P ground at H ground. So H ground, which is the height above ground or our reference level, is then simply whatever the level the sensor happens to be on at initialization. In my case, I'm just keeping my sensor on a desk, so that'll be my reference level. In essence, this formula is really useful for looking in changes in pressure and changes in altitude. For example, an aircraft or drone might use this. It has a runway, and we want to see what height it is above that runway or above ground. In any case, regardless of which method we go with, we'll need to filter measurements. So raw measurements will be typically very noisy, even if they've been processed already by the barometric pressure sensor. We need to maybe bandwidth limit them, low pass filter, high pass filter, and so on. We'll typically go with just a simple low pass filter. The question is, do we filter our raw measurements of pressure, or do we apply this formula first and then filter, for example, our final altitude or altitude difference? It depends on how you initialize your filter. Essentially, P can be very large. We saw, up to about 100 kilopascals. So if the filter starts at 0 and has a very slow time constant, it might take ages to settle to the mean of where P is usually at. Whereas H, which is our height difference actually, so H minus H ground, always starts off near 0 in this equation. In any case, it doesn't really matter because it's a linear mapping, but you have to make sure, with filter initializations, and that the filter is fast enough if you don't initialize it. Now moving on, how do we actually apply a filter? And there's many different ways. There's much better ways, for example, Butterworth or higher order filters. But for this simple example, we're going to use a first order digital low pass filter. Remember, we'll be doing this in the digital domain on an STM32 microcontroller. So we need to design a digital filter. I won't be going over much detail here. I do have an IIR filter theory and implementation video. That's video number 32 for your reference if you want to learn more about IIR filters. We'll be going with a very simple IIR, so a filter employing feedback, and it's going to be first order. We have n, or lowercase n, as our sample number, x is our input, y is our output, and we have a single filter coefficient, and we'll call that alpha. That's anywhere between 0 and 1. Essentially, our current output, y of n, is alpha, our filter coefficient, times the previous output, so y of n minus 1, plus 1 minus alpha times x of n, which is our input, our current input. So you can see if alpha is 0, y of n is simply x of n, so we have no filtering. If alpha is 1, that output is simply the previous output, so we get maximum filtering, so no pass-through from the input. So we can vary alpha from 0, which means no filtering, to 1 to maximum filtering, depending on what our needs are, and we'll play around with that a bit later. I've done some Bode plots in MATLAB of these filters, and I've just chosen 0.1, 0.5, and 0.9 as coefficients. And you can probably guess heavy filtering is 0.9, which is the yellow trace. Keep in mind this is an absolute scale and frequency on the bottom. So dropping from 1 very rapidly down and attenuating quite a lot at even low frequencies. If we turn up alpha to 0.9, somewhere in the middle of 0.5, you can see the red trace is that frequency response. And 0.1, we get very light filtering, which is this blue trace. And here's the phase also as well, which will introduce some delay, of course. So let's move on over to looking at the hardware and then the implementation for our STM32 device. Before we get started looking at the software, let's briefly familiarize ourselves with the hardware, because we'll need this to then write the drivers, see which I2C pins the barometric pressure sensor on the bottom here is connected to the MCU with, and so on. I have the design for the LittleBrain++ open in Altium, and if you go to my GitHub page, as mentioned earlier, you can get all these files and produce one of these boards yourself. The main microcontroller is an STM32 F411, so a fairly powerful microcontroller, and I've got various peripherals to play around with attached to it. The only one we'll be using today is, of course, this barometric pressure sensor, which is an SPL06001. I believe it's somewhat of a clone of the Bosch BMP180, works in a very similar way. You can either use SPI I2C. For simplicity, I used I2C because this enables me to set this interrupt pin so I can always trigger reads every time the barometric pressure sensor has new data available. So this is connected via I2C2 and this simple interrupt pin to our microcontroller over here. Other than that, we have an LED, which will indicate, okay, that things are working, a 60 MHz crystal, a USB connection, which is useful for relaying data, as well as this Tag Connect debug header, which I'll be programming the device with. The Tag Connect header is pretty cool. As you can see up here, it's a solderless header. You need a special adapter cable, which I'll show you in a second, but it lets you quickly program boards without having to solder an actual physical connector on. And this is the specific Tag Connect cable I'm using. It's the TC2030 with no legs, so I can just plug it in, and you have an extra retaining clip to hold it. Although it might seem a bit pricey to begin with, this is really useful because you never have to solder on a connector anymore. For debugging and programming, I'm using my usual, cheap ST-Link version 2 with an adapter cable for the Tag Connect header. I'll leave a link to the Tag Connect products in the description below. Before we move over to STM32CubeIDE, where I'll show you the software setup and the drivers and so on, let's briefly look at the digital pressure sensor datasheet. We'll be using this to estimate altitude from pressure. So as I said before, this is the SPL06001 and this was available at JLC, so that's why I just took it. It's fairly inexpensive. What we need to see is our supply voltage range, that's compatible with our board, and of course that is, and a pressure range, which is important for us, because it'll also tell us, okay, up to what altitudes can we measure? So up to plus 9,000 meters and down to minus 500 meters below sea level. So this is great for us. This is exactly the range we need for this absolute pressure sensor. We can also see various accuracies, temperature stabilities, and so on. So depending on your application, what precision you actually need in your altitude measurements, this will be very important. I won't be going into too much detail in this video of how to write a driver for the STM32 devices and I2C, but I do have a rather lengthy, almost 40-minute introduction of how to write a driver from start to finish, going through the datasheet and then actual testing. So I'd highly recommend that if you're interested in writing drivers. Here we now are in STM32CubeIDE, and I've done a very, very basic setup of this STM32 F411. In my pinout planning, I've enabled my external crystal, enabled USB, serial wire debug, I2C, the barometer interrupt pin, as well as my LED output pin. The barometer interrupt, if I click on it, is simply an external interrupt pin, and then of course you also have to set up your interrupt controller by going to System Core, NVIC, and make sure XTI line 1 interrupt is enabled. So once we set up this barometric pressure sensor, it'll then trigger or pull variant high, which we can then trigger with an interrupt and perform our read. And I'll show you how to do that in just a second. In GPIO, make sure to go onto your interrupt and make sure it's on rising edge trigger detection. And of course that depends on what you want to be looking at. You can also do falling edge in certain cases. In middleware, because I want to stream data via the USB port, I've enabled USB device and I've included the virtual COM port driver, essentially like a virtual serial port. In clock configuration, my input frequency for my crystal is 16 MHz. I selected high-speed external crystal, the PLL clock, and I'm running at 72 MHz. We don't need much processing power for this. Now we're ready to browse through the main code, and I've pretty much written all of this already from the slides we saw earlier and implemented the ideas we saw. I've included my SPL06 driver, which I wrote, and I'll see in just a second and go over what the functions are in that driver. I have some defines we can play with, for example, the initial pressure sample count, as we said before. When we boot up the device or when we want to measure our reference altitude or reference pressure level, I'm counting, in this case, 50 samples, adding them together, dividing by 50 to give me an average reading. As we saw before, I also have a very simple low-pass filter for this barometer, and this is essentially the alpha value, so the filter constant. Now, the barometer is running at its own sample time, which you can change with the register settings, but I'm also streaming via USB, and this is not happening synchronously. My sample rate of the barometer is about 8 Hz, and I'm sending over data at about 5 Hz to the USB. So not particularly fast. You can go faster, of course, but there's no need for us for this very simple demonstration. For my altitude calculations, or my relative altitude calculations, I of course need some constants. That's the density of air in kilograms per meter cubed, and I'm just assuming a fixed constant, and of course this depends on temperature, altitude, and many other things. Gravity of the Earth, I'm just assuming the Earth's surface on an average, 9.81. Of course, the gravitational constant of the Earth and the density of the air will change, and that'll influence your height or altitude measurement as well. Pressure sea level we don't really need, but we can see that as some sort of baseline. That's about 101.3 kilopascals. Then I'm defining my barometer struct, and we'll see the driver after this. A data ready flag to make sure I can start processing once this is set. Just for me, there was some data count and data rate variables just to see that I'm getting my 8 Hz out. And here we have the main part, which is our process data. I have a variable which contains the initial average pressure, which we sample over the count we want to. Process pressure, so after we perform our low-pass filtering, it's stored in this variable. The relative altitude, so once we apply our formula, which is our estimate altitude in meters, and this is of course relative to the initial level. For USB logging, I'm also storing the raw pressure in pascals, which we can then use to compare to the low-pass filtered value to see how much our filter is affecting the signal. Let's just jump down to int main for a second. After our initialization, I initialize the SPL06, which is our barometric pressure sensor, and in case that doesn't work, I simply turn on an LED and say, okay, I'm not going to run any further. To start my triggers with the interrupt, I need to perform a single read. This will then start my interrupt loop. So once my interrupt is triggered, remember we are trying to read if this pin goes high, so a rising edge detect, the hardware abstraction layer of STM32CubeIDE nicely provides me this callback, and I just check if it's the barometer interrupt pin that is fired. I set my data ready flag to 1. Back in my main while loop, I then check that data ready flag, and then I can read my data from the barometer. which also then clears the interrupt. I can clear my data ready flag, and then I can call my process barometer data function. I also have a very crude timer running, which then triggers every time we pass our desired sample time for the USB data streaming. In this, I just simply use the virtual COM port, and I've shown this in previous STM32 videos on my channel how to do this in more detail. I'm simply streaming my raw pressure, my process pressure, which is essentially my low-pass filter data, and my calculated relative altitude, all to the virtual COM port, and then toggling the LED so I can see every time I've transmitted some data. Lastly, and maybe most excitingly, this is the process barometer function. I store my raw pressure data, so not filtered. Then I perform my raw pressure measurement. And this is a very simple first order IIR low-pass filter, so a feedback-based low-pass filter. My output is my constant times my previous output plus 1 minus that filter constant times the current. And we saw that from the slides earlier. This if statement here is essentially just during initialization, I count up to whatever sample count I want, add up the pressures, and once I'm done, I divide that by the sample pressure count and say, okay, I've got my initial baseline pressure data. So every time this STM32 firmware starts up, it'll compute the average pressure. And of course, you will have to keep the device on one altitude level while this is happening. But this is fairly quick. So once I have my initial altitude calculated average, once I have my current filtered raw pressure measurement, I can subtract them from each other, divide by the density, and divide by the gravity on Earth. Of course, I can't forget my minus sign because as you move the pressure sensor up, the pressure decreases. So it's an inverted relationship, so to speak. And then I store that in the relative altitude, and that's in meters. And that's all there is to this main code. Just briefly, the SPL06 driver, very straightforward driver. I have my initialization function, and I have a read function and a struct to just store all of my data. I'm checking the device ID, making sure, okay, can we even read from this I2C device? I'm reading calibration coefficients, so I'm just following the datasheet. It tells me I need to read out all of these calibration coefficients to make sure I can calibrate depending on temperature, pressure, and so on. I set it to 8 Hz with 8 times oversampling. I do the same for the temperature configuration. I want continuous pressure and temperature measurements. This is what this register rate is doing here. And lastly, I'm enabling the data ready interrupt. So only generating interrupt when the pressure data is ready. I don't really care about temperature data at this point because this is a very crude implementation and I want this to be active high. In my read function, I'm just reading 6 bytes of data, so 3 for pressure and 3 for temperature, converting the raw uncalibrated pressure and temperature over here, and then applying the calibration as per the datasheet to get my temperature in degrees C and pressure in Pascal. Finally, I'm clearing the interrupt status register. Without this, this won't work because it won't re-trigger the interrupt. So this is very important, and that's all there is to this driver. I've uploaded the code to my STM32 device via the Tag Connect probe, and initially let me just check that the interrupt is indeed firing and I'm getting data through. So I'm using my Digilant Waveforms Analog Discovery Pro connected via USB, and I'm in scope mode. So let me just probe the pin, and you can see I'm getting periodic firings of the interrupt, and this should be, about 8 times per second. So this seems pretty close to start with, so that's a really good sign. It looks like we're reading data out. I can of course also put my STM32 device in debug mode and set a breakpoint. I'll just leave it run for a bit to start the initial calibration, and then I'll just set a breakpoint in my process barometer function. So I can double click and you can see it's paused, and I've variables monitored on the right side here. So the pressure in Pascal is about 100,000, and if you remember, pressure at sea level nominally is about 101,000. So this seems like a pretty reasonable value. The temperature in degrees C, I've had this board on for a little while, so it's around 33 degrees. It's pretty warm here, it's the summer currently, so yeah, maybe something around that. That seems about right. That's a really good starting point. If I hover over my initial pressure calculation, we can see we have about 100,000 as our initial pressure, so that seems about right. We divided by the right amount of samples. Raw pressure contains one value. Pressure value, which is a low-pass filter, contains a slightly different one, so that makes sense as well because they're not going to be identical. The relative altitude, and this is in meters, remember, so this will be scaled down quite a bit. I haven't moved the board, so it's about 0.5 centimeters, so 0.005 meters. So this seems about right to start with. So we're getting fairly sensible values out. Let's move over and try and plot this data, and first we'll look at the difference between low-pass filtered and raw before we move on to the altitude measurement. I've now uploaded my code again, and this time I'm just essentially sending over via USB the raw and processed data. So raw first and then processed, which is quite simply speaking just the low-pass filter data. I usually use PuTTY or HTerm just to make sure I'm getting data out. My serial port is COM5, and I can click connect, and you can see 5 times a second we get our raw and processed data. Okay, so this looks good, it's changing, it seems about right. So let's open the serial oscilloscope. So I've uploaded the new code so we can measure, or rather see, the differences between the low-pass filtered and not low-pass filtered raw pressure. To do that, and to also make sure the scaling is okay, I've subtracted, or rather inversely subtracted, the initial pressure from both measurements, so they're about centered about 0, and we can easily see what's going on with the scales involved. I can open Serial Oscilloscope, which I'll leave the link to in the description below. Click on my serial port 5, and at the bottom we can see the sample rate is 5 Hz, which is exactly what we wanted. Then we go to Oscilloscope, channels 1, 2, and 3, and then adjust the scale. So here we have two traces showing. We have green and red. So green is the low-pass filter data, and red is the raw data, so to speak. The way I can see that is because during very high frequency movements, so you see when it's jumping around here, the red trace is always slightly higher. That in turn means that the green trace, or the low-pass filter, is attenuating these high frequency movements. However, during fairly steady state, for example this decline here, the green trace follows the red trace fairly well. Remember, we aren't applying a lot of filtering, so our filter constant is set to about 1/4. What we can already notice, I mean this is now in the units of pascals, we can see there's quite a bit of movement. I've not moved the pressure sensor one bit so far. So there'll be random walk, there'll be bias, there'll be drifting over time. So we can already see maybe pressure sensors on their own aren't the greatest thing to rely on. It also depends on what kind of accuracy we want, which we'll see later in the altitude or the relative altitude measurements, because pascals initially don't tell us very much. But this is just to examine the low-pass filter. I can zoom out, I'll start moving my pressure sensor, or rather the board, up, and you can see because I've inverted the pressures, I'm climbing up, which is what we expect, and I move the board down. Now I'm putting it on the table again, which should be around 0, and you can see it doesn't quite reach 0. So it keeps drifting, moving around, but we're staying within a certain band. So I can move it below the table. After initial jump, it actually goes below 0. So our initial function or pressure sensing seems to work in some way. So let's just increase the value of alpha to see how much filtering maybe we can increase to get rid of some of these fluctuations. So I've changed my low-pass filter alpha from 0.25 to 0.9, and let me just upload that code. And now let's look at our traces again. What we really notice, by increasing the low-pass filter, the coefficient quite a lot, the green trace is far smoother. It's basically ignoring a lot of this high-frequency content, which is what we expect. So this steady state behavior might be a bit nicer, but of course this now introduces lag into the signal, some sort of delay. So if we want fast updates, want to see quick changes in altitude, this might not be the most optimal. So let me just start playing around with it. I'm lifting the device up. As you can see, there's a lag during movement, and at steady state, this seems okay. But as soon as I move it away from steady state, there's quite a bit of lag between the green and red trace, so the filtered and raw data. So at steady state, of course, this is really nice, what we want, but for fast movements, this isn't optimal. So this means we should probably turn down our filter coefficient a bit. Somewhere in the middle, 0.5 is probably a good bet. So this is now with a low pass filter setting of 0.5. You can see again we have much more high frequency noise, but the green trace, the low pass filter trace, does follow the raw data much better. So if I start moving it around, I move it below my initial level, you can see these are a much closer match, and we've attenuated some of the high frequency noise. So this seems like a fairly good compromise. But remember, this depends entirely on your situation. Sometimes a very slow rise time or very heavily filtered signal is preferable to something like this. But with our low-pass filter being tested and it working, let's go over to altitude estimation. So now I've uploaded the new code, and all I've changed is that I'm just transmitting one float variable, which is the relative altitude. So we can see, okay, what kind of drift do we get for altitude if I'm just letting this board be on the table? What if I move it around? What kind of accuracy can we expect? So back to the serial oscilloscope, opening my port, and I'm just getting one value out. So here we are just plotting the relative altitude, so relative to wherever the board started. And let's just watch this for a while. I'm not touching the board, I'm just letting it sit here, and we can see the walk or the random walk this sensor is performing, or the measurements are erroneously moving about our relative altitude. Notice the scale on the left, we have a scale of meters, so 0.0, 0.02, so this would be centimeters then. So you can see this random walk, it goes below and above this 0 line, and it hopefully is constrained between plus and minus 10 centimeters, even though you can see there's a tendency for this measurement to drift upwards, and you can see it's starting to drift down a bit as well. So for the way we are calculating the altitude, with our constant coefficients, we're not doing temperature or density of the air compensation, we're getting about, plus minus 10 centimeters. So let's see what happens if I lift it above the table. Let's see if I can try and lift it about 10 centimeters above and change my scale, and you can see it's moved up to about 20 centimeters. I can move the board down again, and it takes some time for it to settle, but it's moved back down to about 10 centimeters. So this change needs to be about 10 centimeters, which is how much I moved. I can also move it down. So below the table, you can see we have these initial transients. So we're not getting, I'm just doing it by eye, trying to move it down 10 centimeters, but we definitely see a movement, but you might get an error of plus minus 5 or 10 centimeters. Again, just laying the pressure sensor on the table, you can see it keeps trying to climb to a mean of about 10 centimeters. Even though initial starting point, as we saw on the left, was around 0. So it's definitely drifting away from its center. And we are fluctuating quite a bit. We could, of course, apply more low-pass filtering, and we can also set thresholds. So if it's between 0 and 5, we just clamp that to 5. If it's between 5 and 10, we just clamp that to 10, and so on. So we can probably hard gate this pressure signal, this altitude signal, to get something more reasonable out of this. Also keep in mind this is a very inexpensive, very small pressure sensor. So you can get pressure sensors of higher quality and more precision. And also you can, of course, improve the code and filtering as well. I do hope this video gave you a small insight into how to interface with the pressure sensor and how to estimate changes in relative altitude. I look forward to seeing you in the next video, and thanks again for watching.